Hey, what's up everybody? Welcome back to Quantum Mechanics for the Working Professional. This is another problem solving session, and today we're going to be covering some of the problems from both chapter 1 and 2. Precisely, we're going to look at problem 1.8 and problem 2.4. That is to say, we're going to look at kind of what happens when you stack two Stern Gerlach machines together. Let's get started. So you might recall the generic quantum state, psi, is given as the linear combination of two vectors up and down, alpha up plus beta down, where alpha and beta are constants. We've defined the states so that they are the eigenstates of the spin operator in the z direction. That is to say, when we measure spin along the z direction, which you can do, for example, with a Stern Gerlach machine, the end result is either going to be one of two options, either spin up or spin down. So the operator SZ acting on spin up gives h bar over 2 times spin up. And of course, the action of SZ on spin down gives minus h bar over 2 spin down. Other things that we've learned about in both the lecture and in the previous problems is the existence of another spin operator where we can measure the spin in a different direction, spin x, say, which is related to the Stern Gerlach machine's device, the spin z operator, by simply rotating that magnet, rotating that device by 90 degrees from the z direction to the x direction. So if z is up and down, x could be right towards the camera. We also found two all other states that, we've given different names at different times, but I'm going to call them up x, down x, such that spin operator acting on, say, up x is, of course, h bar over 2 up x, and on down x, it's minus h bar over 2. We have originally, I think they were introduced as like phi 1 and phi 2, or if you like, phi 1 and phi 2 tilde. These are normalized states. The relationship between these two states was just simply a matter of a rotation, right, in basis. So in other words, whereas the up state was given by the column vector 1 and 0, and the down state was given by the column vector 0 and 1, the up x state is given by the column vector 1 over the square root 2, 1 and 1, and the down x state was given by the column vector 1 over square root 2, 1 and minus 1. And just to be absolutely crystal clear about what we're doing, I'm now going to add a z label to our up and down states, our classical one, these ones here, boom, so that we understand kind of clearly what's going on. So this gives us, four separate vectors, each of which they come in pairs, and they are both kind of orthogonal to one another. Meaning what? Meaning that up z with up z is equal to 1, but up z with down z is equal to 0. Similarly, up x is equal to 1, but up x with down x is equal to 0. Amusingly, if we were to try to mix those states together, up z with down, say, x, what is that, right? Well, that's 1, 0 times 1 over the square root 2, 1 and minus 1. So that's just 1 over the square root of 2, and so on, and so on. Okay, so now that we're kind of done with a bit of review, what are we going to do today? Today, we're going to explore how the quantum state evolves after we subject it to different measurements. And then we're going to take a bit of a tour on different kinds of randomness in physics and in quantum mechanics. So let's set up the following situation. Suppose that, just as before, I have an oven full of silver atoms that I heat up just like we've been doing. And then further, suppose we collimate the beam in the usual way so that we have a nice, consistent beam of silver atoms pointed at what? At a giant magnet. That's right, at the Stern Gerlach device. So let's just call that device SGZ, because we're measuring, the Stern Gerlach device is measuring spin in the z direction using SZ, the operator. And what happens? Well, of course, the input states are random, so the output states give us two beams, one of spin up, one of spin down, because remember that magnetic field deflected the little tiny spins on those little tiny atoms. Now, what I'm going to do now is put a wall that, right after the spin down case. And then for the spin up case, I'm going to actually focus those spin up particles into another Stern Gerlach device. And let's also have it be in the z direction. So my question for you is, what comes out of that second device? Well, hopefully the answer is obvious. All of the beams going into the Stern Gerlach device are spin up. These are all spin up in the z direction. And because they all share that same quantum state, then the output of the Stern Gerlach, the second Stern Gerlach device, is just going to be 100% spin up particles. Super easy. So just to be clear, let's go through the whole system again. We start with a totally random state, whatever that means. Those are pushed into the Stern Gerlach device in the first case. That measures their spin. We're able to assess whether or not they're spin up or spin down. By measuring their spin, we've changed their random quantum state all into precisely the spin up in the z direction quantum state, that 1z, if you like, that 1 and 0. And that has, that propagates through, and that's just their quantum state now for as far as we're concerned. Okay, so it goes through the second Stern Gerlach device and still up, blah, blah, blah. Great. So now let's change things up and see what happens. So now let's change the Stern Gerlach device. So that hopefully is the answer to problem 1.8. So, but now let's do something a little different. Let's change that Stern Gerlach device, that second one, to measure spin in the x direction. Let's rotate that magnet by 90 degrees and see what we got. So following, again, the logic, we have a random state, whatever that means, that goes into the Stern Gerlach device. It spits out two definite beams of definite spin, definite quantum state. That is to say, each beam coming out of the first Stern Gerlach device has variance equal to 0 independently, right? Good. So spin up beam goes into the second Stern Gerlach device, but this time it's measuring spin up in the x direction, spin and spin down. So what happens? We once again get two beams. Two different beams. We get up in the x direction and down in the x direction. Now, it's a little kind of a cheat because I'm only working on two-dimensional paper, so you have to imagine the beams not going up and down like they did in the first case. They're kind of rotated by 90 degrees. They're going out in those other separate directions, but whatever. This is a schematic. You get the point, right? The point is that the second measurement, we knew that we started with a spin up state, but the spin up state is a superposition of spin up x and spin down x. What? That means, let's review. So spin up x is equal to 1 over square root 2 up plus 1 over square root 2 down z. And spin down x is the same, only with a minus sign. So what happens if we add these two things together? Well, lo and behold, spin up in the z direction is proportional to the sum of spin up in the x direction plus the sum of spin down in the x direction. And that constant of proportionality, you probably guessed it, it's 1 over the square root 2. Good. Now, what is spin down in the z direction? Well, okay, so what I'm trying to assess here is tell you this is the state that we're interested in, because this is the state that the particle comes into the second machine with, and it's equal parts spin up x, spin down x, which is why it gets split up equally into spin up x and spin down x. And in a previous problem, we've learned that the expectation value of spin x for the state up z is 0, which means that it's a bimodal distribution, which in particular means that its variance, the variance of the spin x operator in this state, is maximal for a two-level quantum system anyway. So it's h bar squared over 4. Good. So that's more or less what happens when we chain two Stern Gerlach devices together. We're going to do more of this because I think it really spells out exactly how quantum mechanics and measurement work. And so we'll do this ad nauseum in the future. But for now, I want to ask a slightly different question. What is a totally random state? When we came in to the Stern Gerlach, the first Stern Gerlach device, we said was totally random. It was coming out of the oven. What is a totally random state? Well, we had, I don't know if you recall, but we had said that we modeled a totally random state by alpha equal to beta equal to 1. But that can't be right, can it? Because that's just spin up x. Brother. Next time, we're going to look at just what a totally random state is, because obviously spin up x is not totally random, is it? So stay tuned for that. See you then.